Welcome back to another video. We are talking about the physical application of vectors. Strap yourself in, it's going to be a long one. So I guess here's the joke. Why did the old man fall into the well? I guess it's because he couldn't see that well. All right, here we go. All right, so a couple things that you need to understand. If you are in probably any other school, you probably would have covered this stuff already. If we're talking about physical applications, it's kind of talking about physics. Why are we doing physics and mathematics? Well, surprise, they're related. Physics, the physical application of vectors, the main things that we're going to talk about today is displacement, velocity, and force. Okay, so displacement, when I'm talking about displacement, all you need to know is I'm talking about its position. Okay, it's a particular position. Velocity, all I'm talking about is it's a particular speed and it's got a direction. So I'll write that down because it's going to come in handy later on when, if you already know your stuff with calculus. And then that's all you kind of really need to know. We'll talk more about force later. Let's try to catch it. Okay, so there's no actual notes. It's going to be more kind of modeling questions because I think that's the best way you're going to be able to see it. And I've picked one with displacement, one with velocity, and a couple with forces. So hopefully it gives you a little bit of a start. But again, probably your best way to get good at these is to actually practice HSC questions and yada, yada, yada. You've heard all that stuff before. So let's say a city walks on a 3-kilometer bearing of 15 degrees true. Find how far north she traveled using projection vectors. So this is the key thing here, using projection vectors, because I'm pretty sure you've done questions like this before, where you just use standard trig. But let's just say, for example, the first thing that you want to do with a lot of these questions is you want to name your vectors. Now, I find that that's just a helpful thing to do. I'm going to say let u equal, let's say the vector city's path, right? City's walk. Right, and I'm going to say let j equal the north, I guess, the north kind of vector. Okay, so because we want to find how far north she traveled. So the way that this would work is, let's draw a little diagram. Okay, or maybe let's, sure. I'm going to draw it like this. So we know for a fact that city walked 15 degrees in this direction, and I'm going to call this vector u, okay, because that's what she walked kind of across. And we know that this is 3 kilometers. Okay, now what we want to do is we want to project it onto vector j, which is our north vector, and we want to see how far she ends up. Now, we know that by doing this mathematically, it's going to kind of give us this, what we're really looking for is that length there. Now, we could find this out with trigonometry, but using the projection vectors, it'll look a little bit like this, okay? Because we remember that the projection of u onto j is going to be given by the length of u times cos theta times the unit vector of j. So j, we're just kind of letting be j because it's north. I don't need to make it a unit vector. It's already just kind of its own thing. So the length of u, we know, is 3 kilometers. And we know that cos theta is going to be the angle in between, and they're both tail to tail. So we're sweet. It's going to be 3 times cos 15. And I don't have a calculator. I do. 3 times cos 15 in degrees. That'll be roughly 2. What did I say to 2 decimal places? I'll say to 2 decimal places, 2.90. Because that would be 2 decimal places, and that'll be it. So that means if she traveled 3 kilometers on that direction, the amount that she's traveled, how far north she traveled, is only going to be 2.9 kilometers. Okay, so far so good. Let's continue on using this idea. Now, this one here is where we start to work with velocity. Okay, we're no longer working with just a position, we're actually working with speeds. Now, good news is, same deal. We're going to use projections to help us out here. So a cruise travels in a southeast direction. The speed along the coast is 60 kilometers per hour, and the speed in the water is 100 kilometers per hour. I know that's confusing. We'll talk about that. The question is find the direction of motion and its speed away from the coast. Okay, so first things first, just like every other question, let's label some things. Let's say I'm going to pick X, Y, and Z. I'm going to say let X be speed, let's say along the coast. Let Y be speed in the water. And let's let Z be the speed away from the coast. Away from coast. Okay. Now, all these things kind of sound a little bit weird because we don't often talk about different speeds in the water, but what actually happens is, if I was to draw a little diagram here, we're traveling in the southeast direction. So southeast means if, let's say, for example, there's my coast, the southeast direction is somewhere roughly along that way. Okay, so because that's north, that's east, there's south, and so southeast would kind of be in that kind of bottom right quadrant. Okay, so far we've got that. We know the bird's traveling in that direction, and let's just start labeling some of the things. Okay, this is technically the water, so this would be my Y. Okay, and we know that Y is traveling at a speed of, what did we say? The speed in the water was 100 k's an hour. So we can write that down. Now the speed traveling along the coast is 60 kilometers per hour. So that means along the coast means it's parallel to the coast, which means it's going to be this guy here. Okay, it's going to be traveling at 60 kilometers per hour. Okay, and then the way, I guess, away from the coast, that's going to be, I should have said along the coast would have been X. So this is vector X going down this way. And then the last one here, the speed away from the coast, that's going to be my vector Z. Okay. Now it says what we end up wanting, what we will want to find is, it says we want to find the direction of motion. So the direction of the motion is technically this guy here. If we're talking about from north, we're talking about that. Okay. The other thing that we'll need to find is, we found the direction of motion, and then we also want to find the speed away from the coast. Now the speed, it just means we're trying to find this guy here, which I think is going to be quite easy because I know that's 100, that's 60. So that means Z. Let's talk about speed first. It's easier. The speed is going to be, it's a right angle triangle. So I know it's just going to be 100 squared, which is the hypotenuse, take away 60 squared equals to Z squared. Okay. And that's just going to give me a big number, but I'm pretty sure this would just be Z just going to equal to 80, right? Because it's your Pythagorean triad, 3, 4, 5, 6, 8, 10, right? And so I've just kind of done that. So I can see that my speed away from the coast is 80 kilometers per hour. Okay, there's my speed. Now to find the direction of motion, the easiest way to do this is to, let's find this angle here. And it'll be, well, let's go theta, right? So we're trying to find theta, and that one is just going to use SOHCAHTOA. It's a right angle triangle. Let's say I've got all three sides really, so let's just use maybe 10 will be the easiest. 10 of my angle, theta, is going to be opposite, which will be my 80, over adjacent, which is 60. So to find theta, I'll just take the 10 inverse, and I know that's going to simplify to 4 on 3. And 10 inverse of 4 over 3 is going to give me 53 degrees. That's going to be to the nearest degree. And then from there, if that's 53, the direction of motion, so direction of motion is just going to be 180, take away 53, which I believe is 127 degrees from north, right? That's the direction that we're traveling. That's that 127 degrees. Okay, so as you can see, for a lot of these problems, draw it out. Label what your vectors are. Everything in the question that they give you, label it out, draw it out, and then start working with what you've got. So if I'm trying to find, I guess, a particular thing, I could always project, but in this case here, it was a lot easier just to recognize it was a right angle triangle. It was Pythagoras. It was SOHCAHTOA. Okay. So that would be that. Just a little hint as well is sometimes they'll say the direction of motion. They'll say find the direction of motion away from, the direction in the water, or they'll say from north, or they'll say from the coast. And so those are the little things you have to be careful of when they're asking you, I guess, the direction. Okay, the direction from where. Okay, now moving on, there's a couple more. There's something called the resultant of two vectors. It's just a fancy way to say what happens if we have two vectors at the same time happening. And very simply put, you're just going to sum them together, right? Which makes sense. If I've got two vectors that are pulling on, we normally use this for force. So if we pull with a force on in two different directions, it'll end up being the sum of those two forces, right? And if I want to find the total force, it'll be the magnitude. So I'm making this slightly clear. Let's tackle this question here. Let's say Chiara and Lawrence pull Justin in two different directions. Chiara pulls north at 60 newtons and Lawrence pulls east at 40 newtons. Find the resultant force and the direction. So here again, I'll draw a diagram. And here, most things are kind of labeled. So let's say, for example, there's Justin. And Chiara is going to pull in this direction, and Lawrence is going to pull in this direction. Now we know Chiara pulls at 60 newtons, and we know that Lawrence pulls at 40 newtons. Now, if we were to line these guys up, approximately something like this, we can see here that the resultant force is going to be, and we can, what's nice is I made it north and east, so it's, kind of like a right angle. So because that's nice, the resultant force is actually just going to be, it's going to be, I'm going to write this as 40I plus 60N. Okay. I'll talk about J because we're talking about horizontal. 40, a force of 40 towards the east and a force of 60 to the north, right? So that means 40 in the horizontal, 60 in the vertical. That there is your resultant force vector. So I should probably write that down. That's the vector for it. Okay, so what you would do is if they gave you like a couple different forces that are acting on this one particular object, you would sum them together. Okay, because theoretically this is 40I plus 0J, right? And then plus 0I plus 40, or 60, sorry, plus 60J. Okay, that's technically what it is. Now what's happening is we're going to get this resultant force vector. We've summed it. Now, if I wanted to find the resultant force is basically a fancy way of saying what's going to be that there. Okay, it's going to be the magnitude. So in other words, it's going to be the square of 40 squared plus 60 squared. And that there is going to be 40 squared plus 60 squared. That's going to be approximately 72.1 newtons, okay, to 1 decimal place. Okay, so the resultant force is going to be the magnitude, which I've written here. Okay, total force is the magnitude. Now to find the direction from north, it's going to be nice and easy. All I'm really finding here is if that's north up here, I'm just going to find that angle there because now I'm heading in that direction. So the easiest way to do this is let's label this theta. I can see here that that's 60. That's a nice right angle. And I've got 40 up here. I'm going to work with my nice right angle. Okay. And the way that I'm going to do this is by using trigonometry. So that means I've got opposite and adjacent. Let's use tan theta. So here I can see that tan theta is going to equal to opposite, which is 40 over adjacent, which is 60. That means theta is going to equal to tan inverse of 2 on 3. Just simplifying as I go. And then let's see, my tan inverse of 2 on 3 should be something like 34 degrees to the nearest degree. Okay, so that means from north, that'll be 34 degrees. That there is my direction of the force. Okay, so again, it's this idea, this resultant vectors is someone's pulling in one way, someone's pulling in the other way. Those two vectors can be written as if they were one vector by summing them. And then from there, you can find the resulting force. And you can also find the direction that it's being pulled in. Okay. Hopefully that makes sense. Now we do have one more. So I hope you're holding in tight. If you need to pause it, have a glass of water, do some star jumps. I don't know, relax. When we talk about units of force, we kind of saw it in that question already, but we're going to talk about, I guess, newtons. Now, Newton's second law is something that you'll have to have memorized, but thank the Lord, it's actually an easy one to memorize. It's that force equals to mass times acceleration. Okay, so that's why you've got F equals to ma. That's force equals to mass multiplied by acceleration. Okay, now normally when we talk about the physical applications, normally when we talk about acceleration, we normally talk about gravity. And most times they'll tell you, I think every time they'll tell you what value to use, but they'll generally say 9.8 or 10 meters per second squared. Okay, that'll be that. Now let's have a go at this question here. Oh, looks like I've left this here. Maybe I'll just leave it so we can kind of see what's going on. It says here, a 15 kilogram parcel rests on a plane inclined to 30 degrees to the horizontal. What component of the gravitational force is acting on the parcel in the direction down the plane? Okay, now looks like I've left this in here, but maybe it's a good thing. So what I've done here, the first step that I've done is, maybe I'll just make a little highlight as I go. First thing that I did was I started labeling. I'm trying to talk about what vectors do I need to know. Okay, the first one is I'm going to let I be a direction down the plane. Now, the reason I used I is because you need to be, I guess, used to seeing I as not only the horizontal. Okay, in this case, I'm going to use I for the incline. And you just have to read the question because it changes every time. That's why it's an applied applicable applications of physical applications. Okay. Okay, so I'm going to say I is the direction down the plane. You can kind of see that there. There's my direction down the plane. Okay, now my F is my force of the parcel down the plane. So that's kind of this guy here. So that means kind of that parcel will be drawn towards sliding down that incline. And I'm also going to let W be the force downwards due to weight, because there's a particular weight that's actually drawing it down. Now, the first part of the question is what component of the gravitational force is acting on the parcel in the direction down the plane? So in other words, I'm trying to find that F here. I'm trying to find that component of the gravitational force down in the direction down the plane. Okay, so in other words, this is what this is really saying here is I know that there's a gravitational pulling down. I know that there's a force that's pulling me down the incline, but to find what the component of the gravitational force is, it's actually talking about a projection, because I'm talking about the weight that's supposed to be pulling down is actually now being used to slide across. That's why it's a projection. So that means basically F is going to be the projection of my weight onto the direction of the incline, which is my I. So that's why my F is going to be the projection of W onto I. Okay. So here, what I've got here is your projection formula. If I'm projecting W onto I, it's just going to be, I should have written it here, and I'm glad I caught it. It's going to be the length, or the magnitude, sorry, of W times cos I and cos theta, which is going to be the angle in between, and it's going to be in terms of I. Now here, I know my weight. I said here is a 15 kilogram parcel. So there's my 15, and then my angle. Now I know we talked about 30 degrees, and I know the temptation would be to use 30. 30 degrees is the incline, okay? But the angle in between the weight and the force down, down the incline that's actually 60 degrees. So I had to do a little bit of working out there because, you know, it's a right angle and angle sum of a triangle, complementary, whatever you want to call it. But I had to find out the angle in between the two vectors I'm looking at. That's the angle I need. So it's going to be 60. If you do your calculations, cos 60 will be 1 on 2, a half. So that's why my force down in the direction down the plane is going to be 15 on 2. And technically, I think it'll be kind of like, yeah, it'll be the force. Okay. Now, the way that we've done that, we've got that. There's our force. Now, what it says here is like, given that gravity is 10 meters per second squared, what's the force in newtons? If we're talking about newtons, then remember, force equals to mass times acceleration. And then in this case here, the mass is going to be this. It's going to be the 15 on 2. The on 2 is, remember, because of the incline. And from there, all we do is we just multiply it, mass times acceleration. Our acceleration due to gravity is 10 meters per second. So we're just going to times it by 10. And that's how we will get 75 newtons. So that means the actual force, the units that we use, will go 75 newtons. Okay. So that's how we would turn something that we just had weight, but then we started talking about force due to an incline. That's how we changed that into newtons. Okay, which is a bit different from the question before, because the question before, we were given already the forces. So we just worked in terms of the forces. But sometimes what they'll do is they'll give you, I guess, some information like this with no talk about force or newtons, and they'll want you to find the actual force. And don't forget, force equals to mass times acceleration. My goodness, this was a long video. If you have stayed here to the end, I applaud you. Well done for putting up with me for who knows how long. But I hope you guys kind of get it. If you don't, leave some questions below. Try some questions, go through the HSC papers. These are going to be the ones that you'll see more likely in your HSC. All right. Peace out, and I'll let you guys go. Bye.